The other day I was handed a bottle of IV fluid that I did not recognize. All that was on the label were the contents of the bottle measured in grams per litre. On closer inspection, I identified those contents as salts dissolved in water. How do I figure out exactly what's in the bottle in terms of quantities that I actually understand, such as millimoles per litre or milliequivalents per litre? That's what this tutorial is about, salts and their quantities. Tutorial 2, Salts. This time I will discuss ions in salts and how to calculate the number of millimoles of each component of a compound dissolved in water. Let's start with some preliminary material and some science. The first question is, what is an ion? When an element gains or loses electrons, it carries an electrical charge and it becomes an ion. For example, sodium gains an electrical charge in collisions, so it is positively charged and it's represented by Na+. The additional electron has minimal impact on the atomic mass. Chlorine loses electrons in collisions, so it is characteristically negatively charged and represented as chloride Cl-. Positively charged ions are cations, negatively charged ions are anions. In body fluids, and this is really important, the number of positive charges must always equal the number of negative charges. The cations must equal the anions. Well then, what is a salt? Salts exist when positively charged particles or cations bind up with negatively charged particles or anions. Here we have a single anion combining to a single cation to form a salt. An example of this is NaCl or table salt. The valency is the charge carried by the ion and it's measured in milliequivalents per litre. In this example, both X plus and A minus, the cation and the anion, are both univalent. The charges must always be balanced. In this example, we have a different particle, X2. It carries two charges and it is therefore a divalent cation. In order to form a salt, either a divalent anion or two univalent anions must bind to it. Here are two univalent anions, and they bind to form a salt. An example of this, for example, is calcium chloride, where calcium is divalent and chloride is univalent. So it's CaCl2. Let's return to water. Water, as you recall, is a solution in which other elements disperse or dissolve. It has the ability to dismember compounds, ionizes them, and it also self-ionizes. So here is sodium or chloride or salt, and when it's immersed in water, it dissociates and then dissolves, and it spreads throughout the entire liquid at a measurable quantity. Importantly, water also slightly ionizes to release a hydrogen ion that carries a positive charge and a hydroxyl ion, that's one H plus and one OH minus, that does the same. Now they don't float freely in solution. The hydrogen ion binds to a big globule of water and hydroxyl does the same. And we will revisit this when we talk about acid-base chemistry. And all of this brings us to intravenous fluids. Most intravenous fluids are constructed by adding a number of different salts. Any charged particle that particles that are added must be accompanied by equal and opposite charges. For example, the cation sodium, Na+, must be accompanied by an anion such as Cl- chloride, or lactate, or bicarbonate, or acetate, or gluconate. And now it's time for a clinical scenario. You are called to the emergency department. Richard, 44, has arrived in the ED and he's had a seizure. On the blood gas, his measured sodium, Na+, is 112 millimoles per litre or milliequivalents per litre. You are informed that you need to administer a bolus of 75 millimoles or 75 milliequivalents of sodium. We know so far that the quantity of any substance is measured in moles or millimoles. This patient, Richard, has a deficiency of sodium. So how are we going to correct his sodium deficit? As we have already discussed, When you administer sodium, you must co-administer another particle, an anion, and that anion is usually chloride. And this needs to be dissolved in water. So to treat this patient, you need to administer a salt solution. The most commonly prescribed intravenous fluid is isotonic saline solution, and this contains 0.9% NaCl. That means, of course, 9 grams of salt per litre. Of course, that salt dissociates into its component parts and disperses. The way we measure the quantity of an ionic sodium and chloride solution is to calculate the molality. So, how many millimoles of sodium are in this product? I'm going to take you through a simple approach. Let's revisit the periodic table of elements. We can locate sodium here, it's element number 11, and chloride is over here, it's element number 17. As we have discussed, the atomic mass of each element is more than twice its atomic number. The atomic mass of sodium is 22.9 and the atomic mass of chloride is 35.5. We could round those up to 23 for sodium and 36 for chloride. To figure out the molar content of a salt solution, you need to follow a number of simple steps. The first step is to calculate the number of millimoles per gram of each component. The atomic mass of sodium is 23, and 1 mole of sodium is approximately 23 grams. 1 gram of sodium is 1000 divided by 23, which works out at 42.5 millimoles per gram. Remember this because sodium is one of the most abundant cations in the body, and we will revisit it multiple times. For chloride, we know that its atomic mass is 35.5, and 1 gram of chloride is 1000 divided by 35.5, and that works out at 28.5 millimoles per gram. So 1 gram of sodium contains 42.5 millimoles, and 1 gram of chloride contains 28.5 millimoles. Step 2 is to calculate the molecular mass of the compound. Well, this is relatively easy here because we just combine the atomic mass of sodium to the atomic mass of chloride. So there we are, 23 for sodium and 35.5 for chloride, and that works out at 58.5. So that's the molecular mass of NaCl, one particle. Step 3, now that we know the total weight in grams, we can calculate the proportion of 1 gram attributable to each component. We know that the atomic mass of sodium is approximately 23 and that of chloride is approximately 36, and the molecular mass of NaCl is 58.4. If we divide the mass of sodium by the mass of the salt compound, 23 divided by 58.3, we get 0.4 grams of sodium, or 40% of the entire product in 1 gram of salt. So 1 gram of salt is 0.4 grams sodium, 40% sodium. Similarly, if we divide 36 by 58.4, that's the atomic mass of chloride by the molecular mass of salt. This works out at 0.6 grams of chloride per 1 gram of salt, or it's 60% chloride. Step 4 involves calculating the amount in grams of each component by multiplying the percentage, i.e. 0.6%, times the total quantity. And here we have our saline solution. Remember this is 9 grams of NaCl. Each one of these is 0.4 grams of sodium and 0.6 grams of chloride. And this is just another way of looking at it. The actual weight of the chloride is obviously going to be greater than the weight of the sodium. So to work this out, 9 times 0.4 grams of sodium works out at 3.6 grams of sodium in 9 grams of salt. So that's 3.6 grams of sodium, and 9 times 0.6 grams of chloride equals 5.4 grams of chloride in salt. So 3.6 grams of sodium and 5.4 grams of chloride in that 9 grams of salt. Step 5 is to multiply the number of millimoles by the number of grams. Remember, 9 grams of salt is 3.46 grams of sodium and 5.4 grams of chloride. There are 42 millimoles per gram of sodium. You know that there are 3.6 grams of sodium in NaCl, so multiplied by 42.5 you end up with 154 millimoles of sodium in 9 grams. Likewise, 1 gram of chloride contains 28.5 millimoles. Multiply that by 5.4 and that results in 154 millimoles of chloride in 9 grams. Because sodium and chloride are univalent, there is also 154 milliequivalents of sodium and 154 milliequivalents of chloride in this solution. Going back to our bottle of isotonic saline solution, we now know that 1000 mils contains 9 grams of sodium chloride, and that works out at 104 millimoles of sodium and 154 millimoles of chloride. And of course, 500 mils contains half that amount, 4.5 grams of sodium chloride, 77 millimoles of sodium and 77 millimoles of chloride. Now, if you're down in the emergency department and you've been asked to give this patient sodium to increase his sodium because he has low sodium or hyponatremia, and somebody may hand you this bag, and this is, of course, 3% saline or hypertonic saline solution. Now, you might want to calculate out the sodium and chloride concentrations from this bag. So let's work this out. First of all, let's remember that 3% saline is 3 grams per 100 mils. The conventional treatment, by the way, for using hypertonic saline is to give 150 mils of this. Let's work that problem. We know that 1 gram of sodium is 42.5 millimoles and that 1 gram of chloride is 28.5 millimoles. 100 mils of 3 grams of salt contains 3 times 0.4 grams of sodium, remember 40% sodium, and 3 times 0.6 grams, remember 60% chloride, of chloride. That equals 1.2 grams of sodium and 1.8 grams of chloride. 1.2 grams of sodium is 42.5 times 1.2 or 51.3 millimoles per 100 mils of sodium. And 1.8 grams or 28.5 times 1.8 or 51.3 millimoles per 100 mils of chloride. 150 mils contains 1.5 times 51.3, and that is 77 millimoles of sodium and chloride. In 150 mils of 3% saline, there are 77 millimoles of sodium and 77 millimoles of chloride. Incidentally, where I live, there's sea, and people swim in the sea and they always say it's very salty. Of course, there's no salt in the sea. It's actually sodium chloride and various other electrolytes that's dissolved in there. And on average, there are 28 grams of sodium and chloride salt per litre of seawater, and that works out at about the same as 3% hypertonic saline. We can run through the same process for 7.5% saline. I would suggest that you just pause this video and work this out yourself, how much 7.5% saline is required to give the patient 77 millimoles of sodium. But if you haven't done that, just follow me through here. 1 gram sodium, 42.5 millimoles, a gram of chloride, 28.5 millimoles. 100 mils of 7.5 grams of salt contains 7.5 times 0.4 grams of sodium, as we've seen before, 7.5 times 0.6 grams of chloride. So 3 grams of sodium and 4.5 grams of chloride. 3 grams of sodium is 42.5 times 3, or 128 millimoles in 100 mils. And of course, chloride is exactly the same, 128 millimoles per 100 mils. Now we know that 1 mil is 1.28 millimoles, so in order to get 77 millimoles, you will give 60 mils. To give 75 millimoles of sodium and chloride to Richard, who's hyponatremic, and that's a very inconvenient number, so I would suggest giving 77 millimoles. We can give 500 mils of 0.9% saline, 150 mils of 3% saline, or 60 mils of 7.5% saline. And they're all obviously approximations. Let's review this tutorial. What we covered here was what a salt and an ion or electrolyte is, how to calculate the number of millimoles per litre of each component from the number of grams of salt dissolved, and the different sodium and chloride concentrations in isotonic and hypertonic saline solutions. Next time, I will discuss the principle of osmosis, the distribution of water and solute in the body, and the concept briefly of osmotherapy. You can move on to tutorial 3 now, or join me to look at some examples of calculating out the ionic contents of IV fluids.